Welcome to solverfy.
Using Newton's method, we will approximate the fourth root of 75 correct to 8 decimal places. So remember, Newton's method is a method with which we calculate or approximate the root of a nonlinear equation of the form f of x equals 0, that is, a general nonlinear expression equated to 0, and this method helps us approximate solutions to this equation. And the idea behind the method is that we start with some initial guess, x naught, and if we have something like this is the function, this is the root we want to approximate, and we start with let's say, some initial guess is x naught relatively close to the root in some way. So we take the tangent line to the curve at that initial guess. That is, we take the tangent line at this point. Let's say that tangent line will cut the x-axis at some point, which will be the next iterate, and we repeat the process. We take tangent line at that new point, and we continue that way. And if we can see in this small sketch, we are going to be hopefully we will be approximating to the root or approaching the root of the nonlinear equation. That's equivalent to saying that we are calculating a zero of a function. So here we are asked to approximate the number. So the question is, which is the nonlinear equation to apply Newton's method? What we gotta do before applying Newton's method is state the following. We have the value x is the number fourth root of 75. It means that x to the fourth is equal to 75, and then x to the fourth minus 75 is equal to 0. And now we have an equation, a nonlinear equation, where we can apply Newton's method. And what happens if we found an x which satisfies this equation? Well, we do the inverse process. We have this equation, and then this implies this. We can take, in this step here from here, we can take the fourth root because 75 is a positive number. And so these equations are equivalent, they are the same, that is, we can go from one to the other. So it means that if we solve this nonlinear equation, we will have a value x which must be equal to the fourth root of 75. So, sorry, I just put this here, it's not correct. Okay, so we have to solve the nonlinear equation. We find the value fourth root of 75, and the proof is here. The two equations are equivalent. Well, that said, now we know that our function f of x is x to the fourth minus 75. Its derivative is 4x cubed, and the derivative is needed because this idea I have explained here, when we made the calculations of the tangent line at the root or point of intersection of the tangent line with the x-axis, we get something like this. The new iterate is equal to the previous one minus the function at that previous iterate over the derivative at that iterate. So this is a way of advancing the iterates. Using the previous one, we use this formula where we use the function and its derivative. And doing the calculations, we get the next iterate and we repeat the process, as we said in the graph. And that for n greater than or equal to 0, it means we gotta have an initial guess for the root. We can obtain that guess maybe analyzing this equation or the function, or having a graph of the function some way. So for our case here, as we are calculating the fourth root of 75, and the idea behind Newton's method is that the initial guess be close to the root in some way. What we can see here is that we can think about an exact fourth root of a number which is close to 75. For example, 81. 81 is exactly 3 to the fourth. That is, the fourth root of 81 is 3. And 81 is not far from 75, it's 6 units away. It means that if we start with this value, we should be close to the fourth root of 75. So a good initial guess for our problem is 3. And now you applied Newton's method. In this case, Newton's method got to be programmed in some language to do the calculations. The iterations are updating the iterates using this formula, and that's all. But there are some things we gotta consider. That is when the method is gonna stop. Generally, we use two conditions to stop the iterations. One of these conditions can be that two consecutive iterates are separate from a small distance, that is this condition here. This number is small in some way, which we get to precise in the code. Another way is that because we are solving the nonlinear equation f of x equals 0, we can check also this, if the function evaluated at an iterate is also small. But we can combine both of those conditions. And with these conditions, we stop the iterations. And here, for the quantity to be small, is where we decide how many decimals we get. And putting a small number as the accuracy here, we get more correct decimals. The other things we got to check on in our code is that this denominator here is not null in the sense of numerical null. That is a small number in terms of the calculations in the computer, not as a mathematical zero. Well, if we start at 3 with a small accuracy, that is, we put, for example, 10 to the negative 13 or 12, we'll get almost 15 decimals of accuracy. And when Newton's method converges, it converges quadratically, that is, it's rapid convergence. And here, with an accuracy of, let's say, 10 to the negative 14, that is, we use that number to compare these quantities. And initial guess of 3, we need 4 iterations. In fact, it converges very quickly. 4 iterations to obtain an approximation of the fourth root of 75 with 13 correct decimals. That is much more than was asked if you want. And the value is approximately equal to 2.9428 3095 638 2712. In 4 iterations, there is a very fast convergence of this method for this function x to the fourth minus 75 and initial guess of 3 with an accuracy for double precision of 10 to the negative 14th. We have double precision, meaning that we have around 14, 13, 14, 15, not 15, maybe between 13 and 14 correct decimals. In fact, I have checked with the calculator in different ways, and we have all 15 correct decimals here. And the important fact is that we have calculated that using a very simple function, in this case a polynomial function, x to the fourth minus 75, with very clear and neat derivative for x cubed. And it means that it's a very effective way of calculating numbers. And of course, in the case where the method converges, because in that case it converges quadratically, that is very fast.